record on.
Okay. And okay, I'll try to. I cannot think to too many things at the same time. So you have to push it when it starts.
No, it started now because it says on.
Oh, record on. Okay.
Yeah, it's been confusing to refresh.
So you take care of the light. No, I start with the blackboard, so don't worry. Ah, yeah, you can turn it on. This one doesn't work. Sorry? We exchange position. So be quiet. I have an eye on you. Professeur Docho. So I will. Does this work? Yes. So what I want to do is continue what I was doing yesterday. I remind you that I was talking about tissue fluidization by cell division. And what I was discussing at the end of last lecture is the isotropic component of the stress. So d sigma dt, and sigma, which is the coming from the trace of the stress, is just minus the pressure. So sigma is minus p. So I gave you two results for that yesterday. The first one is d sigma dt equals k, where k is the compressibility, v gamma gamma. This is the divergence of the velocity, or the trace of the, yes? The light. He tried to turn it on, and it didn't work. Ah. Sorry. He's very nice, so don't. Okay, so kv gamma gamma minus rho times kd vd. So this I got by some kind of empirical argument telling that the variation of only the variation of sigma internal counts. It has to be proportional to rho and kd for cell division, and the prefactor I call d. dA is the same prefactor associated to cell death, and dA, with the sign I chose, dd is positive and dA is negative. Now, for the same thing, just by assuming that there is an equation of state, I found that d sigma dt equals kv gamma gamma plus another term, which is minus k kd minus ka. That's assuming that there is an equation of state. And of course, the results would be the same. So these two formulas should be compatible. And you see that they are compatible only if dA is equal to minus dd. So I'll call dA equals small d. Now, this is pretty physical. dd is the pressure I put in the system when I make one cell division. dA is the pressure, the negative pressure I take in the system if I make one cell death. But if I make one cell division and one cell death, the mechanical state of the tissue should be the same. That's more or less what this is telling to you. That if you make one cell division and one cell death, you go back to the original mechanical state in the tissue. Then I can take the d out here, and I have a relation between k and rho d. So provided I do that, these are the two same equations that I derive by different ways. This one by assuming that I had an equation of state, and this one by hand waving on how cell division should occur. So I'll use this one, and what I want to do is go close to the homeostatic state. So I want to work in the vicinity of the homeostatic state. Sorry, I didn't see you.
What do you think that this relation is actually fixing? Is it fixing the magnitude of the active stress, or
That gives you a relationship between the compressibility and the force that each cell division
yeah, but I mean, if I imagine a tissue, I would assume all these quantities to be fixed.
but they are fixed, but they are related. For instance, both of them, it means both of them depend on density, for instance, because the compressibility should depend on density. That's what it tells you. So in my mind, I'm more used to the compressibility. So in my mind, it fixes D. Because I kind of don't know what D is. Compressibility is something which is well defined. It's D sigma d rho up to a factor of rho. Okay? So the homeostatic state is a place where the tissue is at steady state, so where the cell division rate is equal to the cell death rate. So at the homeostatic state, at the homeostatic pressure, the cell division rate is exactly equal to the cell death rate. What I want to do is an expansion around that. So I will write that Kd minus Ka of sigma is something proportional to the pressure minus the homeostatic pressure. And then what I told you is that if I increase pressure, the cell division rate decreases. So there's a minus sign here, and the prefactor I'll call kappa bar. So that what this kappa bar tells you is how the growth rate depends on pressure. Now, of course, I want to keep my variable here, which is sigma and not p. So this is just K bar sigma plus pH. And at the homeostatic state, sigma plus pH is equal to 0, and I'll call that sigma bar. So let me write back this equation here. D sigma bar dt equals K compressibility times V gamma gamma minus K kappa bar sigma bar. So if you just look at this equation, this is 1 over a time. That will be the relaxation time. So the longitudinal relaxation time is tau equals 1 over K times kappa bar. And then I can switch this term on the left-hand side, and I multiply everything by tau. So it's tau d sigma bar dt plus sigma bar equals K times tau V gamma gamma. So this looks like the Maxwell equation. Sigma as a viscoelastic behavior with a relaxation time which is tau. So there is a viscosity here that I call zeta, and if you plug in tau, zeta is just 1 over kappa bar. Now, this equation is a bit strange. I don't know how many of you are familiar with traditional viscoelasticity. Usually what you study is a shear stress. And the shear stress has a relaxation time, and you get a Maxwell equation for the shear stress, which is that. But if you take a standard liquid, the pressure doesn't relax. The pressure, if there is no velocity gradient, should stay constant. What this tells you is that if there is no velocity field, the pressure relaxes. It relaxes in such a way that sigma bar goes to 0. Now this long derivation tells you the same thing as my small drawing of the other day. If I wait for a steady state, the pressure always reaches the homeostatic pressure. If this term doesn't exist, this relaxes to 0 over a time tau, and the pressure always relaxes to the homeostatic pressure. Cells divide and cells die until the pressure is equal to the homeostatic pressure. And there is a longitudinal viscosity that I call zeta. Okay. There's one limit which is interesting, which is what happens if the tissue is incompressible. If the tissue is incompressible, the density is constant. And the conservation equation just tells you that rho times divergence of V is equal to rho Kd minus Ka. So if the tissue is incompressible, the divergence of V is Kd minus Ka. So if I have a growing tissue, what I'm telling you is that for an incompressible growing tissue, the divergence of the velocity is non-zero. It's finite, and it's exactly equal to the growth rate, which is something a little bit unusual. There is a source term here that you don't have in classical hydrodynamics. So the hydrodynamics of growing tissues is different because of this source term here. Of course, if the tissue is incompressible, the pressure is just a Lagrange multiplier that ensures the incompressibility, and I can calculate it as a Lagrange multiplier. So sigma So that's what happens for the pressure, or for the what I will call the longitudinal component of the stress. Of course, I have to worry about now what I call the traceless part of the stress. So I'll call that the transverse. So the transverse stress I call sigma tilde alpha beta, and it has, like the longitudinal stress, an internal part and an elastic part. So I have to check where I put the alpha beta. I put them here. So it's sigma whenever I put this tilde, the trace of the stress is 0. So for any of these stresses, sigma alpha alpha tilde is equal to sigma and this one as well. So, yes? Should one worry? No, because I put right d here, and this is a convected derivative from the beginning. And if you look at what I did last time for the density, I explicitly put only the term ensuring convection here. So this is invariant by translation here. Yes, sir, but not for the longitudinal part. So what he is saying, I don't know if all of you are aware of that, is of course I want a theory which is invariant by translations and rotation. Now, if it's invariant by translation, it should only include derivatives like this, which mean d dt plus v dot grad. But if you have a tensor, if you want it to be invariant by rotation, you have to write what they call a correlational derivatives. There are several ways to do that even. So I don't want to talk about that, but it's always behind that. But for this one, I didn't forget anything. I will ignore the correlational derivative in what comes here, just for simplicity, but it's there, in fact. So the easy thing is the elastic stress. So the elastic stress, sigma tilde alpha beta elastic, is 2 mu times the deformation. So I have to take the traceless part of the deformation. So it's 2 mu times u alpha beta. So this is the gradient of the displacement. And I subtract the trace to have a 0 trace for this tensor. And mu is the shear modulus. I don't know how to take it. It's too warm for me. Like and I lost this one as well. I'm a little bit involved to take out your sweater, but it works. Then I can take the derivative of that. So I will take the convective derivative. If I want to do it correctly, I have to do what your colleague is saying. I have to take the correlational derivative. So this tells me that dt of sigma alpha beta tilde is 2 mu times the derivative of the deformation. The derivative of the deformation is a shear rate tensor. So I will have the shear rate tensor of which I take out the trace. This I call v tilde alpha beta, and v tilde alpha beta is 1/2 of d alpha v beta plus v beta v alpha minus, in 3 dimensions, it's 1/3 delta alpha beta. So that takes care of the elastic part. Now I want to look at the internal stress. So the first thing about the internal stress is that this is a stress which is due to cell division and cell death. The absolute value of the stress is not very well defined, but the change of the stress as a function of time is well defined, because it changes only if there is a cell division or a cell death. So what I will write is d sigma dt. Now this is a tensor without trace. So it has to be proportional to a tensor without trace. So what I have to do is find where in the tissue I have a tensor without trace. Now, one way to define a vector in the tissue is to look at the orientation of cell division. So for each cell, when it divides, I can define an orientation of cell division that I will call P. Now, if I have a vector, it's easy to make a traceless tensor. So this is a unit vector. And I will call that the orientational I'll call that Q alpha beta. It's P alpha, P beta. And then I have to make it traceless, so I have to subtract minus 1/3 delta alpha beta. There are several ways to define an orientation in a cell. I define it as the orientation of cell division. You can also take the nucleus. There is something called the Golgi Apparatus. It's always close to the nucleus, and that defines a direction. Most of the time, this is the same direction that you would define from cell division. So I won't worry too much about that. So the first thing I claim is that I must have Q alpha beta here. Now, if the cell, if the tissue has no stress, of course, P has a random orientation, and then when I average, and I want to average, if the orientation is random, this will give 0. So if the tissue is oriented, this is not 0. If the tissue has a random orientation, on average, this is 0. And then I will do the same thing as for the longitudinal part. I will put a minus sign. I will claim that it's proportional to rho, because each cell is likely to divide. And then there's a term which is the rate of cell division, because this stress appears when a cell divides. And then there is an amplitude. And there is the same term. Now, for the isotropic part, it's what kind of obvious that dA and dd have opposite signs. Here it's not obvious to me, so I don't have any ideas on how dA and dd should behave, whether they have the same sign or not the same sign. Now this relates the internal stress to Q alpha beta. Now what do I do with Q alpha beta? Before I'll tell you what I do, I have to tell you of an experiment. I have a movie, but I don't want to only show that. I'll show it to you afterwards. There is a nice experiment that was done at Institut Curie by somebody called Mathieu Piel. And what Mathieu Piel was doing is that he was putting cells on elastic sheets, so pieces of rubber, and he was watching them divide, and then he was pulling on the piece of rubber when the cell divides. So if you extend the piece of rubber, you let the cell divide, it always divides along the direction where you pull. Then he did some kind of crazy things. He let it start to divide, and he pulled in one direction, and the cell was, if it started dividing in another direction, it was rotating. He was pulling in one direction, he started to divide in this direction, and he was pulling in the other one, and it was rotating. The main point of this, for a single cell on this elastic sheet, is that the orientation of cell divisions is coupled to the local stress. Now, what I'm looking at here is the stress in the tissue, and cell division is coupled to the total stress in the tissue. Now I will do the most naive thing that I can do. I will say if sigma alpha beta, the total stress is not too large, I will expand Q alpha beta in powers of sigma, and I will only keep the linear term. So I will write that Q alpha beta is sigma tilde alpha beta over some typical stress values that measures the coupling between the stress and the local orientation of the cell. Now, if I put that back into here and I sum with this, I will get the total stress. J'ai pas entendu ce que tu as dit. No, they're not tensors. The whole tensorial character is here. No, they are numbers. Sigma is a number. It's the trace of the tensor. So they were numbers. And here, they are numbers because the tensorial symmetry I take into account with this factor here. What I'm kind of saying with that is that in the tissue, there is only one tensor with zero trace, which is Q alpha beta. So whenever I have a tensor with zero trace, it has to be proportional to that. Oh. No, okay, yeah, but in the end, when I wrote my phenomenological equation, I had dA and dd, and these weren't tensors, they were numbers. When it has no indices, it's numbers.
And what are these?
For the longitudinal part, I showed you that they are related to the compressibility of the system. For the transverse part, they have to exist because of my symmetry argument, but I don't know what they are exactly.
For the longitudinal part, when you wrote sigma, d sigma internal dt
Yes,
equal minus rho kd dE plus ka dA.
yes.
So minus rho is because you need rho.
Yeah, I want it to be proportional to.
Exactly. Then kd is the rate divided
Yes.
by k is the rate of depth.
And each of them, they have the pressure that the cell exerts on the neighbor when it pushes. It's homogeneous to a pressure. These ones must exist by kind of a symmetry argument, but I don't exactly know what they are. Yes?
Is there the sort of uncoupling of the internal stress to U alpha or V alpha beta?
No, because I want to describe this. I mean, it's either V, I should use either V alpha beta or sigma alpha beta. In a sense, I want to describe the tissue either by the stress or by the velocity field. So that will come when I complete the problem. But I could do it by putting V alpha beta here. It turns out that it's more transparent if I do it this way. But I don't want to mix the two. So what I do is I take the elastic part, which I wrote somewhere here. I take this and I sum all of these. So I get d sigma alpha beta dt equals minus. So I have sigma tilde alpha beta over sigma 0 times all of this, rho d tilde A plus 2 mu V tilde alpha beta. So I play the same trick as before, and I get the same Maxwell equation. The stress has a relaxation time, which is all of that, and a term which is proportional to V alpha beta, so there is a viscosity in there. So let me write it by introducing the relaxation times. I will write the Maxwell equation. Which says that d sigma is equal to 2 mu So that's a standard Maxwell equation. If you take a complex fluid, so any kind of polymer, for instance, this is the simplest viscoelastic equation that can describe the viscoelasticity of any of the complex fluids. What it tells you is that if you create a deformation, at short time, I can integrate with respect to time. This term doesn't count. So at short times after the deformation, the response is elastic, and I have the shear modulus, which is mu here. And if I wait long enough meaning beyond this time tau, the system flows, and there is a viscosity, and the viscosity is just mu times tau A. So at short time, there is a solid behavior with a modulus, shear modulus mu. And at long times, there's a liquid behavior with a shear viscosity eta equals mu tau A. So that's kind of simple. is like a normal Maxwell fluid, except for numbers. So I want to try to put numbers on that. What I told you is that the shear modulus is something like 1,000 kilopascal. So the shear modulus is 1,000 Pascal. That's what we discussed yesterday. Now I have to estimate this relaxation time. The only thing I can do is say there is KD here, and that's what fixes the time scale. So the best guess I can do, and in most cases it will be true, is that tau A is of order of 1 over KD. So tau A is like the cell division time. So it's 1 day. So the only thing I can do is work with international units. 1 day is 10 to the 5 seconds. And then I want this times this, and that gives me the viscosity in Pascal seconds, which is the international unit. Eta is 10 to the 8 Pascal seconds. So it means, yeah, if I wait for a day, the tissue will flow, but it will flow with a viscosity which is huge. I mean, this is kind of an overestimate of the viscosity. I could have taken a smaller modulus and things like this, but the viscosity of water is 10 to the minus 3. So the viscosity of the tissues is 11 or 10 orders of magnitude larger than the viscosity of water. So there is a viscoelastic relaxation time. I have to wait 1 day before it flows. And then I have this huge viscosity, and it flows infinitely slowly. You have to remember that for the experiment I will show you later. You will see values of the velocity which are awfully small because of this very high viscosity which is here. So that's kind of the basis of what I wanted to do today. Now what I want to do is show you examples on how you can use these equations. And the first thing I want to discuss is what is the diffusion constant of a cell in a tissue. So what I want to do is take a tissue like this, label one cell, and follow it as a function of time. And the assumption that I will make, which is reasonable, is that the cell follows the local flow of the tissue. So the velocity of the cell, V cell of t, is just the velocity in the tissue at the position of the cell. So it's V of R of t. So that's what I will assume. Now, if I know the velocity, I know the position. So if the cell starts at the origin, R of t is sum from 0 to t of V of R dt prime. And then if I want to calculate the diffusion constant, what I need is R squared of t. So I'll write that down. So R squared of t is sum from 0 to t dt1 dt2, and I will write it Vc just to avoid too long things. T1 times Vc of T2, and that will average over the noise in the tissue. Now you can transform this equation by methods which are standard. It's just massaging this equation and write it as R squared of T equals sum from 0 to T dt prime dt double prime V V of T prime now the correlation function of the velocity, because the tissue is time invariant, doesn't depend explicitly on T and T prime. It only depends on T minus T prime. So this is just V C of 0 T prime minus T double prime. Now you know what you do if you want to calculate, and this is standard in liquid state theory. This correlation function decays fast, so you can send that to infinity. And if you send that to infinity, you just read the diffusion constant. The diffusion constant is such that R squared is 6 times dt. If I let this go to infinity, this will be a constant. So it gives me the diffusion constant d is 1/3. This is to make the 6. That's what I want to have here. Sum from 0 to plus infinity. And then I can go back to the velocity in the fluid, V of R of 0 at time 0, V of R of T at time t dt. So I almost didn't do anything. The only thing I did is I said that the position is the integral of the velocity, and assuming that this correlation function decays fast, which is true in most of the cases, I mean, there's absolutely no problem with that. Then this is what I want to calculate. So if I want to calculate that, I need the velocity in the tissue at a given position at a given time, and at this position and another time. Now the way to do that is to take Fourier transforms. So I will define V of R and T is sum dq over 2 pi cubed. This is my definition of the Fourier transform. E to the IQR V tilde of Q and T. And then what I will do, I will plug that in here and plug that in here. So it tells me that the diffusion constant is d equals 1/3. So I will have two integrals over two wave vectors. dq over, I didn't close this, dq over 2 pi cube and then the average, so I will have E to the IQ R of T e to the minus IQ prime R of 0 times V of Q and T. I will put the V tilde of Q and T. I will put the complex conjugate here of Q prime and 0. And I close that, and I have to integrate the dt's there. So it became very nasty. Now what I will do here is some kind of uncontrolled approximation that people are used to do in all these fields of liquids and colloids. I will do something that I will call the mode coupling approximation. Now the mode coupling approximation is to say I have the product of the average of two quantities to calculate. This one depends only on the positions. This one depends only on the velocities. And I will write that the average of the product is the product of the averages. So I will consider that the velocity and the positions are not coupled. So I will do something like this. Then I have two averages to calculate over the noise. This average that involves only positions, and this average that involves only velocities. The easy one is this one. Oh, before I say that, the average of the velocities will carry a delta function in Q minus Q prime. So for the linear series that I will do afterwards, there will be a delta function of Q minus Q prime, which means that Q will always be equal to Q prime. So this is just the average of e to the iq r of t minus r of 0. So who can tell me what that is? It's much simpler than that. If I assume that the probability distribution of r of t minus r of 0 is a Gaussian, this is just e to the minus dq squared t. This is a particle diffusion with a diffusion constant, which is d. So this is what I should get. Then I have this one. So I have to write v of q and t, v tilde times v tilde star of q prime and 0. So as I said, this has a delta function. So it's only non-zero if q is equal to q prime. So there is a delta of q minus q prime. There's a factor 2 pi cube, just for fun. And then there's a function of q and t, which I will call g of q and t. Now if I put all that in the diffusion constant, what I get is d equals 1/3 sum 0 to plus infinity dt. I get rid of one of the integrals because of the delta function. So sum dq over 2 pi cube e to the minus d q squared t times g and that's it. Now, until this point, before I did my mode coupling approximation, which to me is more like mode decoupling, but that's how people call it. So before I replaced the average of the product by the product of the average, this formula was exact. Then I made this non-controlled approximation. My only justification is that I know that for colloids, even if they are rather dense, this works pretty well. So although this is an approximation, it's known to work pretty well. D I don't know, but this is what I calculate. So this is a messy equation for D. And then the only thing I need to know is G of Q and T. But G of Q and T is the time correlation function of the velocity in the tissue. So how do I calculate that? way you can calculate that is you write the equations of motion in the tissue, the one I gave you, the force balance, plus the equation for sigma, which is a trace, plus the equation for the traceless part of the stress. You assume that on average there is zero velocity. You linearize this equation, you add noise, and then you can calculate that directly. So I won't do that because it would take me a long time and I will mess it up every 2 seconds. The only thing I want to tell you is where do I put noise? So in the tissue I have 2 variables. I have the local density that I call rho, and this is given by the conservation equation. And I have the stress in the tissue or the velocity in the tissue. So the noise that I already talked about is the noise in the conservation equation. So it's d rho dt plus divergence of rho v equals kd minus ka, but kd minus ka depends on the distance to the homeostatic state, plus noise. So I'll call this noise psi of t. No, this is not psi, this is psi. And I already, so psi depends on t and on the position, psi of t and r. And I already told you what the correlation function of the noise is, psi of t and r, psi of t prime and r prime, average, is delta of t minus t prime, delta of r minus r prime, times rho times kd plus ka this time. And what I want to do is calculate the diffusion constant because it's easier at the homeostatic state. Now, this is multiplicative noise because this depends on position and this depends on position. If I want to linearize everything, I can replace this with the average density. So the general problem is quite complicated. The one I want to solve is pretty simple. I assume that the density is constant for these terms. So that's one source of noise. The second source of noise comes in the equation for the stress. So the one that I just wrote, tau A equals, so 2 eta v tilde alpha beta plus noise. And I won't write the noise down. Oui. Am I okay in doing the Gaussian approximation here? Oh, it means that the velocity doesn't have a too long correlation time. That it goes straight and turns, and it's valid at long enough times that the viscosity, that the velocity becomes uncorrelated. That's what it means. Now, in practice, everything is consistent. This term is almost always 1, except if you go to ranges of parameters which are not physical, you can replace this by 1. Because this, what makes the integral converge is this one and not this one. So the simple way to, the complicated way to do it is these will decay exponentially, so you can calculate these integrals and then you compare whether this term counts or not as a function of the diffusion constant. In practice, you can ignore that and say it's 1. And the correction is very small. And then you have to worry about the fact that the velocity is not correlated over 2 long times. But in a sense, that's what I'm telling you. If the decay time of the viscosity is the shortest one, what counts is the long times in the integral, and I can assume that the distribution is Gaussian. All this will be valid at times k is larger than this, or of order this. Even larger than the viscous time as well. Although this one I can keep as viscoelastic. There's no problem with that. And you know how to write the correlation time of the noise for a viscoelastic system. Now, what we did, because this is what we did in simulations, we assume that there is a fictitious temperature, and we put thermal noise here. The condition that it should be larger than the cell division time is okay. Larger than the cell death time is a little bit messy because it means you follow a cell, but you can only follow it until it dies. So what you have to look at is cells that live long enough, that they live long enough than the larger times than the average cell death time. This is how you can calculate the diffusion constant. So you can do that explicitly. And if you do that explicitly, you get two things. You get the correlation function of the density, and you get the correlation function of the velocity. And the correlation function of the velocity is just this g of q and t, which is here. And I insist on the fact that this term is almost 1. It doesn't count. So if you do that, what you get for the diffusion constant over 3 pi a, sorry, there is no eta, times kd over rho plus the temperature times rho absolute value I. Squared. And this is it. So there are two terms. Each term corresponds to one type of noise. This term is generated by this noise, which is here, and this term is the thermal noise that I put in the stress. Now, why did I put noise in the stress? The idea is that the cells don't stay the same with time. They fluctuate, their shape fluctuates, their volume fluctuate, and the best way we found to describe that was to put noise in there. But in my mind, what this describes is shape fluctuations of the cell. Yes? Oh, I said I would do it at the homeostatic state, so Kd is equal to Ka. So what will the real answer is Ka plus Kd, of course. No, it's not. Yes, there could be. So what I will show you in a minute, at least in our simulations, the diffusion constant is well defined. And there are also experiments that measure a diffusion constant. People did that in cell aggregates. They follow it as a function of time. So diffusion constant is very small, but still the cell diffuse. Yes? Who is speaking? Sorry. So from that you say rho is rho 0 plus a delta rho, which is a function of q. V is small. You calculate V and delta rho as a function of the noise. Then you calculate VQ, VQ, and you average over the noise. And you calculate rho Q, and you average over the noise. And you take them at different times. And then what you get is this, and the density correlation function at time 0 and at time t for a wave vector q. So it's kind of standard. You just decompose them in Fourier modes, and then you linearize everything, and you get them as a function of the noise. You take the square, and the only thing you need is the square of the noise. Okay?
Where do you need the density correlation?
Sorry?
Where do you need?
I don't need it, but you get it for free. You need it to calculate the velocity correlation function. By the way, I put noise here. I didn't write the longitudinal equation, the equation for the pressure, but it's equivalent to this one. So I don't want to put the same noise twice. So I consider only one of these equations, but this is equivalent to the longitudinal one, the one I showed you in the beginning. Yes? So, yeah, no, that's okay, good, good question. So what I'm saying is the way we chose the noise is we chose the thermal noise for a viscoelastic liquid at a temperature theta. Now, the way you do that is you calculate the response function, you apply the fluctuation dissipation theorem at the temperature theta, and it gives you the noise. But if you write the noise for the stress, it's delta correlated. I'll show you in a I mean, I'll show you simulations. I won't show you experiment, but I'll show you simulations. Yes? You have to speak louder. I'm a bit. Yes? Oh, I do two approximations. I assume the mode coupling here, and then this term, I assume that the distribution is Gaussian. It has D here. Oh, D is the one you are calculating. Because the average value of R of t minus R of 0 squared is just 6 dt. Okay? So I make it kind of self-consistent. I assume I know D. I calculate that. The problem with the mode coupling approximation is this is not a systematic approximation in the sense that I don't know how to calculate a correction to that. Even if I want to do messy calculation and stuff, I don't know how to do it. My only justification is that people have done that for years and years, and it seems to fit experiments pretty well. And there are huge numbers of work in dense colloids and systems like this, and this works well. This is the only justification I have. Who is, oh, sorry. In the last what? No, because I put a complex conjugate and it makes it, I don't like the plus. But I agree, it's a question of taste. Yes? So I write this equation, I write this equation, I write the equation for the longitudinal stress, then I write the force balance equation, which is d alpha sigma alpha beta equals 0. And from these three equations, I get the velocity correlation function and the density correlation function. Because I can calculate the velocity and the density as a function of the noise. And if I linearize, there are linear functions of the noise, so the square is like the correlation function of the noise. Okay? Other? No? Okay, so I'll show you. So Julia, the only thing I can do is put the screen back. So let me go back to this experiment that I was talking about. So this is a cell which at the initial time is put on this substrate, and then they stretch the substrate, they stretch it by 30% even here, and they wash the orientation of cell division. So the way you wash the orientation of cell division, you image the mitotic spindle and you look at the orientation of the mitotic spindle. So you see here this cell deforming and the mitotic spindle goes in this direction. It's not perfectly oriented, but it's pretty much oriented. You do it many, many times. You do statistics, and the maximum is perfectly in the orientation where you stretch. As I said, then in the middle, they started stretching in the other direction, and they rotate the mitotic spindle. I don't know what happens to the poor cell if you do that, but it does what you want, which means it always orients in the direction where you pull. So it's not the same condition as I'm looking at. I'm looking at a cell in a tissue. This is an isolated cell on this plastic sheet. this is the best I can do, and I'm deeply convinced that there's an interplay between cell division and stress. So uh, so that's the same question as Ricard, which means I have the choice to describe a material. I have the choice to decide that the fundamental variable is the strain, or that the fundamental variable is the stress. And what I get in the end is a relationship. It's a differential equation, but still it's a relationship between stress and strain. So if I were expressing everything as a function of strain, of course I would get something slightly different, but then if I transform everything back into stress, I would get the same thing. I haven't done it, but it's kind of obvious to me. Everything is linear at this level. Can you speak louder? Also, the rate of cell division, here I coupled it to the longitudinal part of the stress. And KD is depending on sigma. That's what I said. I said that if I'm close to the homeostatic state, this is proportional to sigma plus the homeostatic pressure. Now, if the tissue has an orientation, if the tissue is what biologists call polarized, then I could also have the traceless part of the stress here, because I could put sigma tilde alpha beta p alpha p beta. We did that in certain cases. It didn't bring any new physical effects, so this is why I'm ignoring it. But the only thing I want to have is a scalar in there. So all the scalars that you can think of are okay. But for an isotropic tissue, what I did is the only thing you can do. And same thing, instead of talking about the pressure, I could talk about the density. Turns out to be simpler if you talk about the pressures and the density. Ricard.
Do you know if people know the biological mechanisms by which cells orient in the direction of pressure, by which they divide more or less depending on stress?
So I asked this question to many people. I guess it goes a lot via adhesion molecules. I mean, when you stretch, you stretch the adhesion molecules, and then there is a pathway that goes back to cell division. That's what I kind of understood. Then it means it's not the same, but there are adhesion between cells in the tissue, so I kind of would guess that it's not too different. In one case, it's integrins. In the other case, it's cadherins. Oui, Olivier. Yes, sir. Yes. Yes. Yes, because the velocity of a molecule of water is more like the sound velocity, which is much larger than. Yeah, but if you start to talk about colloids, for instance, this is a good approximation again. That they are moving, they diffuse, or they can be convected. I assume that there was no flow, no average flow. No, the only flow is due to fluctuations. In this stuff, the only source of flow is fluctuations. And I have thermal fluctuations which are here, which, of course, this is a fictitious temperature that I can tune the way I want. And I have these cell division fluctuations. And you find them back in the result. This is the cell division term. And as Francesc was saying, this in fact is KD plus K8 over 2 that comes in here. And this is the temperature term that comes from this. So, okay, that's what I want to show you next. So this is presentation. Okay, so these are simulations. I'll tell you in a minute how we do the simulations. There are cells, individual cells in the simulation, and we follow the individual cells. Now, this is, so we do it for many cells, and we average S squared is a displacement, what I call R squared, as a function of time, and this is the answer to your question. At least on average, it's perfect straight line. So there's no need to go to super diffusive or sub-diffusive or things like this. And these corresponds to different cell division time or cell death time because they are equal, because this is at the homeostatic state. So the way this is done is we grow a tissue, then we put it at the homeostatic state. So we have a tissue that keeps the same size, and we follow cells one by one. We average R squared as a function of time, and then we change the homeostatic state. So we go for a different KD and a different KA because I want to do it at the homeostatic state. And when I change K or KD, I have these different values. Then what's done here is D. I don't want to go into the reference state, which is something that would take me a long time, as a function of KD, and we change the parameters. So the parameter, there's a parameter I will tell you in a minute, which is associated to the growth of the cells. There is a parameter which is the adhesion between cells. There's an attractive interaction between cells. And these are the two different sets of points when they are changed. This one is pretty linear. Now, if I'm optimistic, I would say this is a parabola, and this goes like k squared, which I forgot here. No, this is a simulation. This is not an experiment, this is a simulation. Sorry? You have to speak louder. The time units. I don't know what the time units is here. It stops. All these points are a few cell division times, because afterwards there's no cell alive anymore. So maybe 2-3 times the cell division time. This is, the question of the time. How do you rescale the simulation with the experiment? This is why I have these weird reference states which are here, and we rescale everything to one simulation where we put experimental numbers. This is how it's done. Now on this one, I forgot how what it was. Yes. Yes. No, this one, the thermal noise acts only on the transverse component of the stress. That's the only place where I put it. And the reason is the noise in the longitudinal stress is the same as this one. There is a trivial transformation between the density and the longitudinal stress. For instance, if I have an equation of state, the d sigma d rho is the compressibility. And I can transform the density and the longitudinal stress. Still, I need the longitudinal stress because when I write the force balance, it's the total stress that counts. So I have to sum sigma and that. So in the force balance, I have the two noises. I have the cell division noise and I have the thermal noise. No, the temperature I fix arbitrarily. I say there is a temperature here, and I do exactly what your colleague was asking me to do. I take this equation, I add an external force, I look at the stress response, and then I apply the fluctuation dissipation theorem. And that's as if the system were at equilibrium. And in the end, this is not a thermal noise. So one part of the stress has this noise, and one part of the stress has the thermal noise. Could be, that's kind of a random choice. Still, it seems, at least with the temperature that we used, that the component due to the thermal noise is not too important. And you can even do it with a thermal noise equal to 0 if you want. They did simulations like this. Okay? Okay, so this was an example where I introduced noise in the system. I want to show you an example of incompressible tissue where the divergence of the velocity is non-zero. And the one I want to choose is a real problem in developmental biology, which is called epiboly. So the experiment was done in the group of Carl Philipp Heisenberg, who is a grandson of the physicist, who is a biologist in Austria, in Wien now, who studies the zebrafish. Now there is a stage of the zebrafish where there is a big cell which is called a yolk cell, like you have yolks in your egg, and this cell is supposed to provide nutrients to all of the other cells. And at some point, there is a layer of cell that covers this yolk cell, and this phenomenon is called epiboly. So I will try to show you, I have a movie of that, like this. So what you see here, the yolk cell is something like this. This is a layer of cell which is spreading on top of the yolk cell. So it's spreading from the top here, and it's spreading down. And the colored cells are dividing cells. So cells divide, cells stretch a bit, and it almost covers the cell completely. Not quite to the end, and after there is another stage of development which is called gastrulation. It folds back inwards. But Carl Friedrich Heisenberg has studied this stuff extremely carefully. So there are two questions you can ask. First of all, what's the speed of epiboly? If I define an angle here, how this angle increases with time? And the second question that you can ask is, what is the orientation of the cell divisions? And what Carl Friedrich Heisenberg was interested in is, what is the orientation of the cell divisions? So I will show you a model for that which is infinitely simple, far too simple, but which illustrates well what I can do with these systems where the divergence of the velocity is non-zero. I'll tell you what you must add to this, but then the calculations become far more complicated. So that's what I want to describe, this epiboly phenomenon. So the layer of cell, and it's a monolayer of cell that spreads on top of the yolk, is called the enveloping layer, EVL, they call it. The size of this is 200 microns, or between 100 and 200 microns. And you see the time here, it's enormously accelerated, otherwise you will kill me, because these are minutes, so it takes 200 minutes to do the complete epiboly. So from the beginning, you start from a seed here, and to go all the way down, it takes 200 minutes. Now, so this is what I will call 4 epiboly. And I will. You have to do something else or not? So I will try to make a drawing. I'm very bad at that, but so I have my so yolk is these big cells, which is something like 200 microns. This is a cell, but it's not really living, it doesn't divide. It's only there to provide nutrients to the other cells. And then I have this EVL that spreads on top of it, so it spreads from here, and it goes down. So this is the EVL. So there is a reference axis which is this one. And the cells of the EVL move on the surface of the sphere. So there is an angle theta, which is here, and there is an angle phi around here, and everything is invariant by rotation, so nothing depends on phi. Okay, so there is a growth rate and the death rate of the cells. In fact, in these experiments, cells hardly die, so the death rate is 0, at least as a scale, as which I show the pictures. So my assumption would be that the cells are incompressible. So if the cells are incompressible, what I told you is that the divergence of the velocity is equal to k, where k is kd minus ka, but in practice it's kd. Now you have to go to these spherical coordinates. So I have just to look in my notes. The divergence, so the radius I call r. The divergence of the velocity is 1 over r d theta v theta plus cotangent theta times v theta. So the cells spread in this direction. They spread on the theta direction, so v is along theta. Still, there are two terms. There is, so if I look at my tensor v alpha beta, there is a v theta theta, which is this one. And this is v phi phi. The way you have to do that, you have to write the gradient in normal coordinates, transform the tensor v alpha beta into spherical coordinates, and trust the person who did it, Jonas Ranft, but I checked that. I wasn't convinced. It took me much more time than him, but we ended up with the same thing. So if I want the velocity field for an incompressible system, the only equation I have to solve is this one. That will give me v theta. So I could solve this differential equation. There's a smarter way to do it. The smarter way to do it is to apply Gauss's theorem. It's like electrostatic. Divergence of the electric field is a charge, and I can apply Gauss's theorem. So let me do that. So the way I will do that, do I have other colors? Yeah. I will assume that I've gone all the way to here, so that I want to consider this layer only. It has a surface, so there is a radius small r here. Small r is big R sine theta. The area of this small spherical cup here, A, is the solid angle of opening angle theta, so it's 2 pi (1 minus cosine theta). Now, forget about Gauss's theorem. The only thing you need to know is that if cells divide in here, they have to flow out because the tissue is incompressible. So the number of cells I produce is K times A, and this is equal to the flux out of this region. So this is 2 pi R times V theta. Now A, I can plug back A in here and divide by 2 pi, so K, and there is R squared here. K R squared 1 minus cosine theta is R, this is R sine theta V theta, and then you read the answer V theta, so it's K R 1 minus cosine theta over sine theta, and this is 2 sine squared theta over 2. This is 2 sine theta over 2 cosine theta over 2. So this is KR tangent theta over 2. And if you don't trust me, you plug it into the differential equation and you will get the right answer. So that tells me that the velocity is 0, and the larger this small cup, the larger the velocity, because there are more cells that can divide. So that's what it tells you. And I could do that just because I know that the tissue is incompressible. I don't need, when I do that, to write the equation, the force balance equation. Now I said that I was interested in the orientation of cell divisions. Now the orientation of the cell divisions is given by the tensor that I was calling Q alpha beta. This is sigma tilde alpha beta over what I call sigma 0. But sigma tilde alpha beta is just 2 eta v tilde alpha beta divided by sigma 0. So the only thing I need to calculate is a matrix v tilde alpha beta. Now I know v theta theta, I know v phi phi, I just have to subtract the trace. So I calculate v theta theta tilde. I won't do it, I just take the derivative and subtract 1/2 of the trace because it's in 2 dimensions. And the trace is k, so it's k over 2. So I don't know what I did with my notes, but so v tilde theta theta is equal to k tangent squared theta over 2. The off-diagonal term is 0 because there is no flow along phi. So the only other component of this is v tilde phi phi, but I know that the trace is 0, so v tilde phi phi is just minus that. Okay, so this tensor Q alpha beta is this factor is 2 eta k over sigma 0. So what this tells me is that the cells divide along the theta direction because this is the eigenvector with a positive eigenvalue. So what this naive calculation is, what it tells me is that cells mostly divide along the theta direction, and they mostly divide along the theta direction because of the flow that creates a stress that orients the cells. So that's very naive, and then you could make statistics and ask how many cells should divide along the theta direction. If you do this naive model, it doesn't work. Now, there are a few things that I haven't taken into account. The first thing is that the growth rate depends on pressure. I assumed it was constant. But pressure is not the off-diagonal part, it's the diagonal part. Now, if I want to calculate pressure, I have to write the force balance equation. And I won't do it because it's a little bit messy to write it in spherical coordinates. What they did, two of my younger colleagues did that. What they did when they did it is that in addition to the viscosity, that's one source of dissipation, they assumed that there was a friction between the cells, the EVL, and the yield. Then you can modify that. You calculate this Q alpha beta experimentally by averaging over all the cell divisions. And you can compare, and with these two features, they were able to get reasonable agreement. But the point on which I want to insist is the first one, and this is why I did that, is that if you look at tissue hydrodynamics, the divergence of the velocity is non-zero, even if the tissue is incompressible. Now I could make it compressible and things like this. It wouldn't help very much because whenever I add a new effect, I had new parameters. So the more I add, the better I will fit. With this, only it was not good enough. So this is why they did that. Yes?
Ideally, shouldn't you also add some kind of flow alignment term in the relation between Q and V?
Between Q and V alpha beta. At the level that I worked before, this is what I'd said. I said Q alpha beta was sigma alpha beta over sigma 0.
Yeah, but then sigma, in addition to having the viscous stress, maybe we should
Oh. That's an interesting question. This is what I will do tomorrow. What I did here is my tissue is active because I cell division, and cell division consumes energy. But what he wants is to say, but if there is an orientation, there is a stress which is due to the coupling to the orientation gradient, and I haven't put that in. And also there could be active stresses if there is an orientation. So I'll do that tomorrow. Okay? But yes, if I want to make it complete, I should worry about these things. Do I have time or should I stop here? 1 minute? Can somebody ask a question? No, okay, I'll stop here and I'll tell you tomorrow morning how we do the simulations.